We now have under our belt several different units for doing solubility and solution concentration. We have mass to mass, mass to volume, volume to volume, and molarity. And it should come no shock to you that all of these are conversion factors that we can use in figuring out how much solute is in a given amount of solvent, or how much solvent are we going to need in order to figure out how much to get a certain amount of solute. So this table here just shows an example for all the different conversion factors we used of how, all the different units we used of how to use them as a conversion factor. So in the first one, it says a 10% M over M potassium chloride solution. We have to remember what percent means, right? Percent means out of 100, right? Now, when it says M over M, we know that our units are going to be grams and grams. They could be other things. We said kilograms would work, pounds would work, but most people will just leave this as grams and grams. Now, what number goes up top? Well, the 10% means that we have 10 grams out of 100 grams. Now, we are chemists, and so we're not happy just to leave it as grams. We have to know grams of what? And remember, it's grams of solute over grams of solution. What's our solute here is going to be potassium chloride that we just get from our definition up there. And over here, it's going to be over grams of solution. So that's what that percent means. Some people get confused when you've got percentages that are less than 1. So if I have 0.050%, let's say sodium chloride solution, what does that mean? We just copy those numbers there. It's still, the percent means out of 100. Now notice I don't write out of 100% because then I'm kind of saying percent is out of 100%, which is kind of weird. Percent's out of 100. And I just copy this number down here, and it's okay to have a percentage less than 1. You know, it's perfectly okay. We just copy that number. This is a mass. In fact, I didn't do a good job, did I? I should say M over M NaCl. Grams of sodium chloride over 100 grams of solution. And so all of these percentages are going to be out of 100, and you just copy the number out of there. But what's going to be really important is getting the units and the helpers correct so that you've got the right thing going on. Now, as soon as you have 10 grams of potassium chloride and 100 grams of potassium chloride solution, we also have these conversion factors that I wrote down here. We've got 10 grams of potassium chloride for every 100 grams of solution, and the bottom one. Now remember, we don't generally write down the conversion factors till we need them. We just write down one of them, and we can kind of figure out the other one from there when we need it. So same thing for V over V, M over V. We just use the appropriate unit. V over V, we're going to say milliliters of ethanol and milliliters of solution. M over V, specifically grams of glucose and milliliters of solution. The hard one for people is that molarity is not a percentage. And so when we say 6 molar, it's not 6 out of 100. It's just 6 molar is moles per liter. And so you get 6.0 moles of hydrochloric acid for every liter of solution. And it looks like this, 6.0 over 1. If I had 0.5 molar, it would be 0.5 moles of HCl over 1 liter of solution. Now, how can we use these effectively? Well, we're going to use them effectively when we want to say, oh, I've got a certain amount of solute. How much solution do I need in order to get that much solute? So I want 5 grams of sugar in a 20% sugar solution. How much of that solution do I need to do it? So examples are always best. So let's go and do an example first. I want to know what volume of a 10.2% M over V solution would be needed to deliver 36 grams of sucrose. Okay. I'm asking for volume. I've got grams. So I'm going to say 36 grams of sucrose. And I want to know volume. Now, volume is a vague unit. Nobody said exactly what unit I should be using. There's lots of volume units, which allows me to use the one that I find most convenient. Now, if you remember, M over V is specifically grams and milliliters, but not density. Right? It's grams and milliliters. And so I'm going to say my desired unit here is milliliters of solution. How do I know it was solution? Because if you read it, it says what volume of this solution would be needed. And so I know it's milliliters of solution. I write my conversion factor here. The nice thing is if you can figure out your starting info and your ending info, the rest of it kind of works itself out. grams of sucrose has to go on the bottom so it can cancel. Milliliters of solution has to go on top so that it's there. Now, what do I do with this grams and milliliters? That's my M over V. 10.2% is 10.2 out of 100. 10.2 grams over milliliters. Since it was M over V, I know its mass is grams and V is volume. And then specifically, this is going to be sucrose, and this is going to be solution. Now, how do I get that into the thing above? 10.2 doesn't always go on top or always go on bottom. Numbers stay attached to their unit. I've got 10.2 grams of sucrose, and so I'm going to put 10.2 grams where my sucrose is. I got 100 milliliters of solution. I'm going to put my 100 where my milliliters of solution is. I multiply that out. I take 36 multiplied by 100 divided by 10.2, and I get myself 352.94, 2 sig figs here. So I get 350 milliliters of solution is what I need to get 36 grams of sucrose. So that's how we can use it as a conversion. And sometimes the conversions are one step, sometimes they require another step. So here it's how many moles of acid are in 130 milliliters of a 0.287 molar acid solution. Very rarely are our concentrations going to be our starting number. So generally, if you've got a concentration in there, a solubility, that's not going to be your starting information. Because remember, molarity is actually moles per liter, and we don't usually, not always, but don't usually have a fractional unit as our starting number. We usually have a single unit as our starting number. So we have 130 milliliters of what? Of a 0.287 molar acid solution. So it's 130 milliliters of solution, and we want to find moles of acid. So if we didn't know exactly what to do, we'd set this up. We'd put milliliters of solution. We'd put moles of acid. And we'd think to ourselves, well, I've got a problem here. I don't know how many moles of acid are in milliliters of solution because I know molarity is moles per liter. So maybe there's another step I have to do of converting these milliliters to liters to moles. And let's try that instead. So our first step is going to be milliliters to liters. We know this one, a lot of milliliters in 1 liter. And our next one, this one cancels. We want liters of solution here to cancel. We want moles of acid because that's what we're trying to get. What goes in there? That's our 0.287. 0.287 means 0.287 moles in 1 liter, and specifically moles of acid in 1 liter of solution. And so our moles of acid is going to get our 0.287 because numbers stay attached to their units. And I go ahead and I multiply that out, and I get 0.037 moles of acid. 2 sig figs in my answer because I had 2 sig figs there, 3 sig figs here, and so I end up with 2 sig figs. So sometimes it's straightforward, it's 1 conversion. Sometimes it's a little less straightforward, and you get these 2, maybe 3 conversions if you need to get the units to match. So you just have to pay attention to that. All right, next topic, making solutions. What do I mean by making solutions? In general, chemists have a lot of solutions that they make. In general, even a hospital has a lot of solutions they make. Lots of IV solutions, lots of medicines and drugs and mixed compounds that they need to make. And it's hard if you want to make them each individually. So generally what people do is they make a very concentrated solution of something. It's got a lot of whatever they're looking for in it. And then in order to make solutions that have a little less concentration, they take a little bit of this, they put it into a container, and so there's a little bit with a lot in there. They add water, and now what you have is you've got the same amount of stuff in a larger volume. You diluted it a little, and that's the actual solution that you use. And so you find this a lot, that people are making solutions from other solutions. Now, what we have to do is find some math that allows us to do that. Let's just think of something real quick. if I took this thing up here and I put 5 grams of sugar and I had 100 milliliters of solution, then I went and I added 100 milliliters of water, what do I get? I now have 200 milliliters of solution, right? But how much sugar do I have? Well, I didn't add sugar, I just add water, so I still have 5 grams of sugar. And so there's this interesting thing that happens when you dilute stuff. Although you change concentrations, the total amount of stuff doesn't change. Now, I could go into the math behind the equation that I'm about to give you, but essentially what it is I'm going to tell you there's this equation that says C1V1 equals C2V2. This should look very similar from our gas laws, right? P1V1 equals P2V2. Okay. And they are. Here we have C being our concentration and V being our volume. And it just says that my starting concentration times my starting volume. So this guy, 5 grams times 100 grams, gives me, sorry, my concentration. So that would be a 5% solution times 100 milliliters is the same thing as at the end. Here I'd actually have a 2.5% times 200 milliliters. That's the same number. Sorry, that was a little confusing. It's not quite what I intended to say. But it turns out when you take concentration and volume, what you end up calculating is how much solids you have. And so when you take concentration and volume at the end, I still have 5 grams of sugar. And so that's why this equation works. We're going to focus on the equation itself and using it. People call this the dilution equation. And it's used whenever you're diluting something or preparing one solution from another solution. And we'll see a few examples of this as we move forward. Oops. I didn't want to give you that first. All right, let's do one example first. Let's say I have 40.0 milliliters of a 5.0% M over V solution of sucrose. What volume of solution, what volume of 1.0% M over V solution can I make? So I've got 40 milliliters of a 5.0% solution of sucrose. And what I'm going to do is I'm going to dilute that until I get a 1.0% solution. But what I don't know here is my total volume. And that's what I'm looking for. How much of this can I make? And anytime we're making one solution from another solution, the C1V1 equals C2V2 comes to our aid. What I like to do, just like I did in the gas laws, is make myself a table because it helps make sure that these two occur at the same time and these two occur at the same time, and we don't accidentally switch them up. So what did I start with? I started with a 5.0% M over V solution here, and I had 40 milliliters of it. What did I end up with? I ended up with a 1.0% M over V solution at the end, and I wanted to know how much of that I had. Let's manipulate the equation first. We're trying to solve for V2. So what we're going to do is we're going to divide both sides by C2. C2 cancels over here, and I get that V2 is C1V1 over C2. And then I can just copy those numbers from my table. I've got 5.0% M over V times V1 is 40 milliliters divided by 1.0% m over v. Now, how do I type this into my calculator? It turns out that when I type this in my calculator, I do not have to type percents. I don't have to convert the percents by doing hundreds or anything like that. I'm literally going to type in my calculator 5.0 times 40 divided by 1.0. And when I do that, I get 5 times 40 divided by 1. I get 200 milliliters. Sig figs on this one. I just made up this problem as I was going. Not a great problem for sig figs. I had 2 sig figs and most of my numbers here. What did I say? I had 40.0 actually, so I should have written 40.0 on all these guys. 40.0 and 40.0 on that one. So let me correct that in a different color so you can see it. So I had 3 sig figs on the 40, but I only had 2 sig figs on my concentration. So really I only get 2 sig figs in my answer here. Unfortunately, 200 can only be written as 2.0 times 10 to the second milliliters with 2 sig figs. I'll try not to do that to you too much, but I just made up this problem. Right, so I was able to make that much solution. So I started one solution, I diluted it, I wanted to figure out how much I could make. Here's another one that you can try. What volume of an 18.7% m over v solution would I need to make 750 milliliters of a 1.35% solution? So here I know how much I'm making, but I want to know how much do I need to start with in order to make it. So pause it, try the equation out, and see where you go. All right. We know we're making one solution from another solution, so it's a good idea to write down our C1V1 equals C2V2. Write out our little table. What are we starting with? What's our concentration that we begin with? We're beginning with this 18.7% m over v. By the way, our concentration units for C1 and C2, you can use any unit you want. M over M, V over V, M over V, molarity. The cool thing is, as long as the same units on the left and the same units on the right, you don't have to figure anything out, convert anything. You don't have to make the volumes into liters or milliliters or whatever. The equation just works because the units end up canceling. What you can't do is have M over V on one side and V over V on the other. That won't work. But as long as you have M over V on one side, M over V on the other side, we are all good. We don't know how much of this we need. That's what we're calculating. Our new concentration is 1.35% M over V. And our final volume is 750 milliliters. We're solving this for V1, so we're going to divide both sides by C1, so that cancels on this side, and we get that V1 is C2V2 over C1. Copy this from our table, 1.35% M over V times 750 milliliters divided by 18.7% M over V. And like I said before, we don't need to put the percentages or anything like that in our calculator. What I type in my calculator is 1.35 times 750 divided by 18.7. When I type that in my calculator, let's see what I get. 1.35 times 750 divided by 18.7 is 54.144. What are my units? My percent M over V's cancel. I get milliliters. How many sig figs do I get? The 750 had 3, the 1.35 had 3, the 18.7 had 3, so I get 54.1 milliliters. That is A. All right, that's how we use the dilution equation. If somebody says the word dilution, great, they gave it to you, you know to use the dilution equation. However, more often it's a little trickier than that, and you're making one solution from another solution. But we can solve for anything. We can solve for the initial concentrations or the ending concentrations, and we're all good. Here's another one. We have 47.2 milliliters of a 12% solution of hydrochloric acid. How much 1.5% M over V hydrochloric acid can we make with this? Pause it, try it out. No, come on. I know you're getting bored of this, but do it anyway. All right. So C1V1 C2V2. Why? Because we're making one solution from another solution. Our little table. What concentration do we start with? 12% m over v. And by the way, all these examples have been m over v, but they could have just as easily been molarity, v over v, m over m. We're fine. And we started with 47.2 milliliters of that. We want to make 1.50% m over v, and we want to know v2. You solve, you get v2 is C1V1, 12% m over v times 47.2 milliliters divided by 1.50% m over v. 12 times 47.2 divided by 1.50 is what I type in my calculator. And so I have 12 times 47.2 divided by 1.5. I get 377.6. What are my units? My percents cancel. I get milliliters. What are my sig figs? 3, but only 2 here. So I have to round that up to 380 milliliters. Not 38, because 38's nowhere close to 377. 380, then I get answer A up here. All right. Last example. What volume of a 7.5% m over v solution of sodium chloride would I need to prepare 100 milliliters of a 2% solution? Again, pause it. Try it out. It's good practice. I know you don't want to. I know you're like, I kind of got this. We're good. Try it out anyway. Why do I take the time to write it out every time? Because I want you to take the time to write it out every time. What did we start with? We started with 7.5% m over v. We don't know how much of it because we want to know how much. We're making 2.0% m over v, and we're making 100 milliliters of it. I'm going to add a dot here so we get another sig fig, a couple sig figs. All right, plugging it in, v1 is going to be C2V2 over C1 if we do the algebra, and we plug that in. We get 2.0% m over v times 100 milliliters divided by 7.5% m over v. In my calculator, I type 2.0 times 100 divided by 7.5, and I get 226.66666. How many sig figs do I get, and what are my units? Percent m over v cancels. I get milliliters. And sig figs, I've only got 2 here and 2 in my other one, so I get 27 milliliters. Is that one of my answers? Oh, I don't have multiple choice. 27 milliliters is what I find. So what does that mean? It means I use 27 milliliters of my 7.5% sodium chloride solution. I add that to a beaker. So I'm going to draw it here. I get 27 milliliters of it. I add H2O until I get 100 milliliters total. I don't add 100 milliliters because then I'd have 127. And now I've got that new concentration that I wanted, which is 2.0% from my 7.5%. If we were doing lab, we'd actually have a chance to go in the lab and do this. We're actually doing the dilutions, but unfortunately, we're not going to get a chance to do that this time. All right, those are using our concentration units as conversion factors. Just remembering percent means out of 100, and this is a lot of making sure we know which helper goes where and that units stay attached to their numbers. Thanks.